Have you ever really stopped to think about the stuff our world is built from?
You mean beyond just noticing it's there?
Exactly. Like, not just the big buildings, but the everyday things. That wooden door you use every day, maybe the plastic pipes hidden in the walls, or even just the window you look through.
It's easy to take them for granted. They're just everywhere.
Right. But what if I told you there's this whole hidden world of, like, science and engineering packed into each one?
Ah, now that gets interesting.
Imagine this. A piece of wood, right, actually giving you better fire protection than some metals.
That sounds counterintuitive, but it's true in some ways.
Or that the term hardwood, which sounds so simple, is actually, well, kind of misleading.
And that's what's truly captivating, I think. How these materials that seem so, well, basic have evolved, and how they're understood in really specific technical ways in architecture. So our goal in this deep dive, really, is to connect those basic properties you see every day to how they're actually used, their practical applications.
We want you to think a bit more critically about their role, in everything built around you.
Exactly.
Okay, let's unpack this. You might think, yeah, I know wood, I know plastic, I know glass. But trust me, this deep dive is going to pull out some genuinely surprising facts.
Things you might not have considered.
Totally. You might have some real aha moments. We're aiming for a shortcut here, helping you get really well informed about these materials in architecture.
We've sifted through a pretty big stack of sources.
Yeah, detailed stuff from architectural journals, books, magazines, internet resources too. We've tried to pull out the absolute key insights.
The surprising bits, the crucial facts.
This isn't just the basic 101. We're kind of dissecting the information to show you the layers underneath. It might just change how you look at, well, everything around you.
So where better to start than wood?
Right. Nature's original building block. Humans have been using it for, well, forever.
Millennia. And even now, its properties are pretty remarkable.
Our research really brings that out. Its inherent strength, its durability, how light it is for that strength.
And it's easy to work with.
Exactly. That combination makes it such an enduring choice. And, let's be honest, there's that natural beauty, that warmth.
Both visually and to the touch, it does make a space feel different, more grounded maybe.
Yeah, inviting.
Absolutely. And the fact that wood is still used so widely, even with important conservation measures in place.
That is a lot.
It really does speak volumes about its value. So understanding wood, it really has to start with how we classify it.
And right there, we hit that potentially misleading term, softwood versus hardwood.
That's it. This is one of those things that trips people up.
Definitely tripped me up. I always assumed hardwood meant, physically harder wood.
And softwood, softer. Seems logical.
But that's not really it, is it? It's more about the type of tree, botanically speaking.
You've hit the nail on the head. It's a botanical classification, not a direct measure of physical hardness. Softwoods, they come from conifers.
Like pine trees, firs, the evergreens with needles and cones.
Exactly. And hardwoods come from broadleaf trees, the deciduous ones that drop their leaves.
Okay.
But here's the kicker, as you said. You can definitely find some hardwoods that are actually softer, density-wise, than certain softwoods. Balsa wood, for example, is technically a hardwood.
No way. Balsa.
Yep. And interestingly, our research points out that most timber found in the Philippines, for instance, actually falls into the hardwood category.
Even if some of it doesn't feel particularly hard.
Precisely. So the names can be quite misleading if you take them literally for physical properties.
Mind blown. Okay, so if hard and soft aren't about physical hardness, what is the most critical factor for how wood is used structurally? What's the key engineering takeaway?
Without a doubt, it's the grain direction. That is the major determining factor for wood's structural performance.
How so?
Well, think about forces. Tensile forces, pulling forces, and compressive forces, pushing forces. Wood handles those best when they're applied parallel to the grain.
Like trying to stretch or squash a bundle of straws along their length.
Exactly that. That's wood at its strongest. But sheer strength, that's resistance to forces trying to slide parts past each other, like breaking a twig over your knee.
Okay.
That sheer strength is actually greater across the grain than parallel to it.
So it's easier to split wood along the grain than to shear it across the grain.
Essentially, yes. And this means wood is more vulnerable to horizontal shear forces acting along its length, trying to slide the top half past the bottom half than it is to vertical shear.
Ah, okay. That's a huge insight for designing connections and beams, right?
Absolutely critical. You
Yeah.
can't just treat wood as if it has the same strength in every direction. The grain dictates everything.
Fascinating stuff. So a tree trunk isn't just uniform wood, it's structured, with different layers doing different things. Our research breaks it down into two main parts: sapwood and heartwood. Let's start on the outside. With sapwood, what is it? What does it do?
Right, sapwood is the softer, younger outer part of the tree trunk.
Just under the bark.
Exactly. It's located between the cambium, that's the very thin growth layer right under the bark, and the inner core, which is the heartwood.
Okay.
Sapwood is usually lighter in color. Biologically speaking, it's the tree's plumbing system, really. It contains living cells, and it's actively involved in the life processes, like carrying water and sap up from the roots to the leaves.
So it's the working part of the wood, the living tissue.
That's a good way to put it. And because it's biologically active and has that structure, sapwood tends to be more permeable.
Meaning things can get into it more easily.
Yes, it's less dense, more porous, and that makes it less durable, unfortunately.
Yeah.
It's more susceptible to things like bluing fungi, which cause staining, and also to wood-boring insects.
Because it's got more of the good stuff, the nutrients.
Precisely. It's richer in organic matter, making it a prime target.
Okay, so that's the living, working outer layer. What about the core, the heartwood? How does that differ?
Heartwood is the heart of the tree. It's the older, harder central portion.
Is it always darker?
Usually, yes. Often distinctly darker than the sapwood. That color comes from various deposits, tannins, resins, other materials that accumulate there over time as the cells become inactive.
Inactive, so it's not living like the sapwood.
Correct. Heartwood is composed of inactive or dead cells. It no longer participates in transporting sap. Its main job is mechanical support.
Ah, the structural backbone.
Exactly. And because of its composition and those deposits, it's denser, much less permeable, and significantly more durable than the sapwood surrounding it. It has natural resistance to decay and insects.
So you've got the living, vulnerable transport layer on the outside and the strong, dead, durable core on the inside.
That's the fundamental difference. And it has huge implications for how we select and use lumber and how we might need to preserve it. Hashtag tag 1.3. Fundamental properties of wood.
That really paints a clear picture of the inside of a log. So let's zoom out again to wood's fundamental properties, the things that make it so useful. Our research highlights hardness, flexibility, that key strength-to-weight ratio, its surprising fire resistance, color, and then how it reacts to heat versus moisture. Let's take hardness first. How do they actually measure that? It's not just kicking it, right?
No, not quite. Hardness in timber is measured scientifically by assessing the amount of compression or indentation a piece of wood undergoes when a specific standardized weight or force is applied to its surface.
Like pressing a steel ball into it.
Something like that, yes. It's a measure of its resistance to denting and wear. It's about practical durability, not just how it feels.
Okay. And flexibility. Does that tie back to the softwood, hardwood thing we debunked earlier?
Well, flexibility is about how much a piece of wood will bend before it breaks. And interestingly, here, the traditional terms often do align somewhat with the physical property.
Oh. So softwoods.
Softwoods do tend to be more brittle, generally. They'll snap rather than bend significantly. Whereas most hardwoods exhibit greater flexibility, they can deflect more before fracturing.
Which makes them good for different things, obviously. Rigid beams versus maybe curved furniture parts.
Exactly. Or flooring that needs a bit of spring.
Now, the strength-to-weight ratio. This sounds like a really big deal in engineering. Why is it so critical?
It's absolutely fundamental. It defines wood's efficiency as a structural material. Wood gives you incredible strength and load-bearing capacity without being excessively heavy.
Lighter than steel or concrete for the same strength, often.
Often, yes, significantly so. And that property is precisely why it's outstanding for such a huge range of things. Long-span bridges, boat hulls, house framing, even delicate furniture. You get a lot of structural performance for the weight involved.
Okay, here's the one that really surprised me. Fire protection. I mean, wood burns. But our research says it chars, and that charring actually slows the burning and offers protection. How does that work? It seems backwards compared to metal melting.
It does seem backwards, but it's a crucial difference. When steel gets hot in a fire, it loses strength rapidly. It can buckle, twist, and fail structurally relatively quickly.
Right.
Wood, when exposed to fire, forms a layer of char on its surface. This char layer is actually a poor conductor of heat.
So it acts like insulation.
Exactly. It insulates the unburnt wood underneath, slowing down the rate at which the fire penetrates and consumes the core of the timber.
Huh.
So large timber beams, for example, can actually maintain their structural integrity for a predictable and sometimes quite long period in a fire.
Which gives people time to get out.
Crucially, yes, it can provide vital evacuation time and prevent immediate collapse, which is a major, often overlooked safety advantage. It doesn't not burn, but how it burns is key.
That completely reframes how I think about wood in a fire. Okay, and then there's the obvious. Its natural color and versatility with finishes.
And that aesthetic appeal is huge. Wood comes in such a range of natural colors, and it takes stains, paints, oils, varnishes beautifully.
You can make it look like almost anything.
Pretty much. Infinite variety, really. It works in rustic settings, ultra-modern ones. It's timeless.
All right, now for a really technical but super important point for anyone actually building with wood, thermal expansion versus moisture content. Our research stresses that wood doesn't change size much with temperature changes.
Relatively little, yes.
But it changes a lot with moisture changes. So moisture content is the controlling factor for dimensional stability. Why is that the absolute key thing builders need to get right? This feels critical.
It is absolutely critical. This is where the real craft of working with wood lies. As you said, thermal expansion is minor, but wood is hygroscopic.
Meaning it absorbs moisture from the air?
Yes, it constantly tries to reach equilibrium with the humidity of the surrounding air. It absorbs moisture when the air is humid and releases it when the air is dry.
And that makes it change size.
Significantly.
Yeah.
As it absorbs moisture, it swells. As it loses moisture, it shrinks. And these dimensional changes due to moisture are much larger, much more impactful than any changes due to temperature alone.
So if you build with wood that isn't properly dried, or if the humidity changes drastically later.
Exactly. You get problems. Warping, cracking, joints opening up, doors sticking, floors buckling. That's why understanding and managing moisture content, making sure the wood is properly seasoned before installation, and designing to manage moisture after installation is paramount. If you don't control the moisture, you don't control the wood stability. It's still a living material in that sense. Hashtag tag 1.4, defects in wood.
Okay, so moisture is the double-edged sword vital for the tree, potentially detrimental for lumber if not managed. Let's talk about those potential problems now, the common defects in wood. Our research details several, starting with decay, caused by fungi. We know dampness is the enemy, but what's the key insight for preventing it?
Right. Decay, mold, stains, they're all caused by fungi. And yes, they thrive in mild temperatures and damp conditions. Most decay really takes hold when the wood's moisture content stays above its fiber saturation point, usually above 20%.
So keep it below 20% moisture, and you're generally safe.
Generally safe from fungal attack, yes. But here's the really practical takeaway. Wood that is constantly submerged in water.
Like old pilings underwater.
Exactly. Or wood that is kept continuously dry, like timber in a desert tomb.
It won't decay.
It generally won't decay. It's the fluctuating moisture, the cycles of wetting and drying, or persistent dampness above that 20% threshold that allows fungi to thrive. So prevention is all about stopping moisture from collecting and staying in the wood. Proper design, sealing, ventilation, it's about moisture management.
That makes so much sense. Okay, so that's decay. What about checks? What are they?
Checks are cracks. Specifically, they're lengthwise separations that occur across the annual growth rings.
Why do they happen?
They're caused by irregular shrinkage during drying. If the outside surface of a piece of wood dries and shrinks much faster than the inside core...
It creates stress.
Exactly. The circumference shrinks more than the interior, pulling the wood apart across the rings, creating these cracks or checks.
And shakes, they sound similar.
Similar, but different orientation. Shakes are also cracks or separations, but they run between and parallel to the annual growth rings.
Like the layers are separating.
Precisely. It's a separation along the growth layers themselves rather than across them like checks.
Okay, knots. Everyone knows knots. But what are they from a wood structure perspective? Why are they a defect?
Knots are basically where a branch grew out from the trunk. So it's an interruption in the smooth, straight grain pattern of the main trunk wood.
The fibers have to go around it.
Exactly. The wood fibers are distorted, growing around the base of that branch, which is the knot. Depending on their size and type, knots can reduce the wood's strength, make it harder to machine smoothly, and cause uneven drying or finishing issues. That's why they're often considered defects, especially for structural pieces.
Got it. Then there are pitch pockets. Sounds sticky.
They can be. Pitch pockets are well-defined openings or little cavities that form between the annual rings. And, like the name says, they contain pitch, that sticky, resinous substance common in conifers.
So just pockets of resin trapped in the wood.
Essentially, yes. Solid or liquid pitch. They can affect the wood's appearance and how well it takes a finish.
And wane. That sounds simpler.
Wane is simpler. It's just the lack of wood on the edge or corner of a board.
Like the bark edge wasn't fully cut off.
Exactly. It's where the original curved surface of the log remains because the piece wasn't cut perfectly square during milling. It's a dimensional defect.
Okay, last one. Warping. That sounds like a catch-all term for bent wood. But our research breaks it down into 4 specific types: crook, bow, cup, and twist. Can you walk us through those? Knowing the difference seems vital for a carpenter.
Absolutely vital. Warping is any distortion from a true flat plane, and it's almost always caused by unequal shrinkage during drawing. Knowing the type tells you how the wood is misbehaving.
So first, crook.
Crook is when the edge of the board curves along its length. It's convex or concave edgewise. Think of a banana shape along the narrow edge. Makes edge jointing difficult.
Okay. And bow.
Bow is similar, but it's the face of the board curving along its length, like an arch or a dip if you lay the bird flat.
Got it. Cup.
Cup is distortion across the width of the board. The face becomes convex or concave from edge to edge, like a shallow U shape. Bad for tabletops.
Right. And twist. That sounds the worst.
Twist often is the trickiest. It's when one corner is higher or lower than the other 3, so the board won't lie flat at all. It has a kind of helical or corkscrew distortion. It makes joinery incredibly difficult. Identifying these specific warps is key to knowing if and how you can use a piece of lumber effectively. Hashtag 1.5, sawing methods, and their impact on lumber quality.
Wow, so many potential issues. But it's not just about the natural defects, it's also how the log is cut in the first place, right? The sawing method itself has a huge impact. Our research highlights 2 main ways: plainsawing and quartersawing. Let's tackle plainsawing first. What is that exactly?
Plainsawing, which is also called tangential cutting, is the most common method. It involves cutting the log tangent to the annual growth rings.
So the saw cuts are kind of parallel to the outside of the log.
In a way, yes. Commercially, it means the angle between the growth rings and the wide face of the board is anywhere from 0 to 45 degrees. It's generally the fastest and most economical way to get the maximum yield of usable lumber from a log, especially wider boards.
What does a plainsawn board typically look like, and how does it behave?
Aesthetically, plainsawn lumber often shows really prominent, sometimes wavy or cathedral-like grain patterns. Very characteristic figure.
Which can be beautiful.
Absolutely. But structurally, because of that grain orientation relative to the board faces, it's more prone to distortion. It tends to twist and cup more as moisture changes.
Ah, those warping issues again.
Exactly. It also wears unevenly, and you can get raised grain where softer wood wears away faster. Dimensionally, it shrinks and swells less in thickness, but significantly more in width.
So where is plainsawn lumber the best choice?
It's often preferred when you want that distinctive, showy grain pattern. Think wall paneling, certain furniture styles, where the figure is a desirable feature.
Okay. Now, quartersawing. How is that different, and why is it often seen as superior for some uses?
Quartersawing or radial cutting is a more complex process. It involves cutting the log radially towards the center, essentially parallel to the medullary rays of the tree.
So cutting more towards the center, like spokes on a wheel.
That's a good analogy. Commercially, the angle between the growth rings and the face is between 45 and 90 degrees. Often the log is cut into quarters first, then boards are sliced off those radial faces. It yields less usable lumber and is more labor-intensive, so it's more expensive.
But what are the benefits? What does quartersawn wood look like, and how does it perform?
Quartersawn lumber has a much straighter, more uniform grain pattern. In woods like oak, it often displays beautiful ray flecks or tiger stripes, which are highly prized.
And structurally?
Structurally, it's much more stable. It wears more evenly, has less raised grain, and is far less prone to warping, especially cupping. Dimensionally, it shrinks and swells less in width, which is often the critical dimension, but more in thickness compared to plainsawn.
So that reduced widthwise movement is the key.
Yeah.
Why is that so important for keeping joints tight? This feels like a crucial takeaway for quality construction.
That's precisely it. Because it exhibits less overall shrinkage and distortion across its width, quartersawn lumber is highly desirable, even essential for applications where stability and tight joints are critical.
Like what?
High-end cabinetry, fine furniture making, musical instruments like guitars or violins, high-quality strip flooring. In these cases, any movement can compromise the fit, finish, or function. So, that superior dimensional stability makes quartersawn wood the preferred choice, despite the higher cost, when quality and minimal movement are paramount.
It's amazing how just changing the angle of the saw cut makes such a difference. Okay, let's move from the cutting method to the product itself. Lumber. Our research defines it simply as wood used in construction. When you go to buy it, how is it classified by size and finish? And what do you actually get?
Right. When you buy lumber, it's typically classified by its nominal size, measured in inches. You ask for a 2x4, a 1x6, and so on.
Using those nice round numbers.
Exactly. And these nominal sizes usually come in even-numbered widths. 4, 6, 8, 10, 12 inches are standard.
And this trips up everyone new to DIY or building that nominal size, the 2x4. Isn't the actual size of the wood you take home? This seems like a universal point of confusion.
It absolutely is, but it's standard practice. The nominal size is the dimension when the piece is rough sawn, fresh off the log.
Before drying and smoothing.
Correct. After being rough sawn, lumber is usually dried and then plain smooth on all 4 sides. This surfacing or dressing inevitably reduces the dimensions, so the actual finished size is always smaller than the nominal size.
Okay, let's make this concrete. Give us those examples from our research again, showing the nominal versus actual for common sizes. Let's start with dimension lumber.
Sure. Dimension lumber is defined as pieces more than 2 inches but less than 5 inches thick in any dimension your typical framing lumber. Here's how it works out. A nominal 2x4 is actually 1.5 inches by 3.5 inches.
Half an inch less in both directions.
Pretty much. A 2x6 becomes 1.5 by 5.5 inches. A 2x8 becomes 1.5 by 7.5 inches. A 2x10 becomes 1.5 by 9.5 inches. And a 2x12 becomes 1.5 by 11.5 inches. You always lose about half an inch in thickness and half an inch in width from the nominal size after dressing.
Wow. Okay, what about board lumber? The thinner stuff.
Board lumber is less than 2 inches thick and at least 8 inches wide. The same principle applies. A nominal 1x4 is actually 3/4 inch by 3.5 inches.
Only 3/4 of an inch thick.
Right. A 1x6 becomes 3/4 by 5.5 inches. A 1x8 becomes 3/4 by 7.5 inches. A 1x10 becomes 3/4 by 9.5 inches. And a 1x12 becomes 3/4 by 11.5 inches.
Yeah.
It's also worth remembering, as our research notes, that this dress lumber costs a bit more than rough lumber because of that extra processing.
You pay for the smoothness and consistent sizing.
Exactly.
And our research also gives 4 broad classifications based purely on dimension. Can you run through those quickly? It helps understand the range.
Sure. It categorizes lumber by size. Strips. Less than 2 inches thick and less than 8 inches wide. Very small pieces. Board lumber. Less than 2 inches thick but 8 inches or wider. Dimension lumber. Between 2 and 5 inches thick in any dimension. The workhorse framing stuff. Timbers. The big stuff. 5 inches or more on the smallest dimension. Used for posts, beams, heavy structures.
And dimension lumber and board lumber are the most common ones we typically encounter.
By far, for most standard construction.
Okay, size classifications make sense now, especially that crucial nominal versus actual difference. How is lumber measured for sale? We know lengths are usually 6 to 20 feet in 2-foot steps. But the unit for pricing is the board foot. What exactly is a board foot? This is fundamental for buying or estimating.
The board foot is the standard unit of lumber volume. It's defined quite simply as a piece of wood that measures 1 inch thick by 12 inches wide by 12 inches long.
So 1 square foot of wood, 1 inch thick.
That's it. That volume equals 1 board foot.
And there's a formula. Can you give us that again? And then let's meticulously work through those source examples, especially that tricky first one about the 3/4 inch board. I want listeners to really grasp this.
Definitely. The standard formula is board feet, thickness in inches, X, width in inches, X, length in feet, 12. Now let's apply it to the examples, keeping that industry convention in mind for thickness.
Okay, example A. A single piece of 3/4 8x10 lumber. How many board feet?
Right. Following the calculations shown in our source, which reflects that industry convention for thin boards, it uses 1 for the thickness, even though the board is 3/4. So the calculation is 1 inch thick by 8 inches wide by 10 feet long, 12.
Okay.
That comes out to 80/12, which is 6 and 23 board feet. And typically, in practice, that gets rounded up to 7 board feet for pricing.
That's critical. Even though it's only 3/4 inch thick, you pay for it as if it were a full 1 inch thick when calculating board feet.
That's the convention the example illustrates, yes. Very important for estimating costs accurately.
Got it. Example B. 10 pieces of 2 footers of 2 footers by 14 foot lumber.
Okay, here the thickness is over 1 inch, so we use the actual thickness. It's 10 pieces by 2 inches thick by 6 inches wide by 14 feet long, 12.
Let's see. 10 by 2 by 6 by 14 equals 1680 divided by 12.
Comes out exactly to 140 board feet.
Perfect. Example C, 5 pieces of 1 by 4 by 10 inch lumber.
Again, thickness is 1 inch, so we use 1. It's 5 pieces by 1 inch thick by 4 inches wide by 10 feet long, 12.
5 by 1 by 4 by 10 equals 200. Divide by 12.
Gives you 16 and 23, which, like the first example, would typically be rounded up to 17 board feet for billing.
Excellent. So the formula is straightforward, but you have to remember that rule about thicknesses under 1 inch, counting as 1 inch for the calculation. And as we noted, dressed lumber costs a bit more per board foot than rough. It all clicks together. We keep coming back to moisture because it's just so fundamental for wood. Our research stresses that water, essential for a living tree, becomes a problem after cutting. It makes wood vulnerable to pest and decay, unsuitable for building unless it's managed. So let's really dig into the water in the wood. It's not all the same, is it? What are the types?
No, it's crucial to differentiate. There are 2 main types of water within the wood structure. First is free water. This is the water literally filling the cell cavities and the spaces between the cells, like water in tiny pipes or tubes within the wood. Second is absorbed water, also called hygroscopic water. This water is actually bound chemically within the cell walls themselves. It's part of the wood structure at a molecular level.
And that distinction matters for drying, right? How does seasoning, the drying process, work with these 2 types? Which leaves first?
It matters hugely. When green wood, freshly cut wood, starts to dry, the moisture evaporates from the surface first. This creates a moisture gradient, pulling water from the interior towards the surface.
Okay.
During this process, the free water is the first to leave. It's less tightly held and evaporates relatively easily. Only after most of the free water is gone does the wood start to release the absorbed water from within the cell walls.
And that's the crucial part for shrinkage.
That's the critical part. It's the loss of this absorbed water that causes the actual wood fibers, the cell walls, to shrink.
Which brings us to another key concept, the fiber saturation point, or FSP. Our research defines it as the point where all the free water is gone, but all the absorbed water is still there, usually around 30% moisture content. And, critically, shrinkage only starts below this point. Why is FSP such a vital threshold? This feels like the absolute linchpin.
FSP is fundamentally important because it's the exact point where wood's physical dimensions begin to change due to moisture loss. Above FSP, if the wood gains or loses free water, its size and strength don't really change much.
Okay.
But as soon as the moisture content drops below FSP and the wood starts losing that absorbed water from the cell walls themselves shrink. That's when you see the wood actually get smaller, when it can start to warp or check. So understanding FSP is key to controlling dimensional stability and predicting how wood will behave as it dries or reacts to humidity changes later. It's the threshold for movement.
And what about equilibrium moisture content, EMC? How does that fit in?
EMC is the destination, if you like. Wood will keep drying until the moisture vapor pressure within the wood balances the vapor pressure in the surrounding air. At that point, it stops losing or gaining moisture. Overall, it's reached equilibrium with its environment.
And that level depends on the local climate.
Exactly. Our research notes that for the Philippines, the typical EMC range is 12% to 16%. Getting lumber close to the expected EMC before you install it is absolutely essential to minimize shrinking, swelling, and warping later on. It means the wood is acclimatized and stable for where it's going to be used.
So how do we get the moisture out? How do we season green wood? What are the main methods?
Seasoning is the process of removing that excess moisture. The 2 main methods are air drying, the traditional low-tech way. You stack the lumber outdoors with spacers for airflow and just let nature take its course. It's slow, and you have less control over the final moisture content. Kiln drying. The more modern controlled method. Lumber is placed in a large oven, a kiln, where temperature, humidity, and airflow are precisely managed using warm, moist air or steam to drive the moisture out efficiently and evenly.
And our research mentions seasoning checks again here, linking them to the drying process. How do they form if drying isn't done right?
Seasoning checks happen because of uneven drying. If the surface of the wood dries out much, much faster than the core,
The moisture can't move from the inside to the outside fast enough.
exactly. So the surface layer shrinks rapidly while the interior is still swollen with moisture. This creates huge internal stresses, and eventually the wood cracks along the grain to relieve that stress. Those are seasoning checks, a sign the drying was too fast or uncontrolled.
Given all this effort and the risks like checks, why bother seasoning? What are the real-world benefits of using seasoned lumber over green wood? The list on our research is pretty compelling.
Oh, the benefits are huge, absolutely essential for quality construction. First, less risk of decay and insect attack. Drying below 20% MC makes wood much less appealing to fungi and many bugs. Second, major weight reduction. Dry wood can be half the weight of green wood, making it cheaper to ship, easier to handle. Third, increased strength and stiffness. Dry wood is simply stronger. Fourth, and maybe most importantly for finished work, minimal shrinkage after installation. This stops joints opening, doors sticking, floors buckling, things stay put. Fifth, reduced checking and warping. Proper seasoning minimizes those defects. Sixth, better nail and screw holding power. Fasteners grip much better in dry, firm wood. And finally, a better surface for paints and finishes. Coatings adhere better and last longer on properly seasoned wood. It provides a stable base.
That's a rock-solid case for seasoning. Now, within seasoning, what are the specific advantages of kiln drying over just air drying? Why is it often the preferred method, especially for higher quality stuff?
Kiln drying really offers superior control and results. You generally get a greater weight reduction because you can achieve lower, more specific moisture contents. Crucially, you get precise control over the final moisture content, hitting a specific target percentage needed for a particular application or environment. That's vital for stability. The drying time is drastically reduced weeks or days instead of months or years. That speeds up production and construction. The heat of the kiln kills any existing fungi or insects in the wood. It's like built-in sterilization. It helps to set the resins in resinous woods like pine, which can prevent bleeding later and improve stability. And importantly, there's usually less degrade. Degrade means loss of quality during drying, excessive checking, warping, loose knots. Kiln drying minimizes these issues, resulting in more consistent, higher quality lumber.
Okay, so seasoning is the first big defense against wood problems.
Yeah.
But even seasoned wood isn't invincible. What are the main biological threats it faces in service? Our research starts again with decay by fungi. We know moisture is the key, but can you recap the conditions and that crucial preventative insight?
Right. Molds, stains, actual decay, they're all caused by fungi. And yes, they need moisture, specifically moisture content above the fiber saturation point, around 20%, plus mild temperatures to really thrive. Keeping wood below 20% MC is the goal for prevention.
And the key insight.
The key insight is that wood constantly underwater or continuously dry generally won't decay. It's the intermittent or persistent dampness in that critical zone that's the problem. So preventing decay is all about preventing that moisture from hanging around, design details, sealing end grain, good ventilation. It's all moisture management.
Got it. Keep it always wet or always dry, but avoid that in-between dampness. Okay, beyond fungi, insects are a huge issue. Our research details several: subterranean termites, non-subterranean termites, carpenter ants, powder pest beetles, even marine borers. Let's start with the infamous subterranean termites. How do they attack, and what are the prevention strategies?
Subterranean termites live underground in colonies and need contact with moisture. They build distinctive mud tubes like little tunnels made of earth to travel up from the soil into the wood structure.
To get to the cellulose.
Exactly. They eat cellulose wood, paper, sometimes insulation. Their feeding channels typically follow the wood grain, hollowing it out internally. Prevention involves several layers. Creating a physical barrier between the ground and the wood, maybe metal shields on foundation walls, or using termite-proof foundation materials. Also, chemically treating the soil around the foundation, soil poisoning, and using pressure-treated wood near the ground.
And vigilance.
Absolutely. Regular inspections under and around the building for those mud tubes are critical. If you find them, you need to break the tubes immediately and treat the soil to stop the infestation.
So a multi-pronged defense. What about non-subterranean termites, like drywood termites? They don't need ground contact, right?
Correct. For them, the primary defense our research highlights is using wood that's been preservative treated, preferably full-length pressure treatment. Since they live entirely within the wood, surface treatments aren't enough. Good sanitation, like removing dead wood near the house, and structural design that minimizes exposed wood can also help, but treatment is key for long-term prevention.
Okay. And carpenter ants and powder pest beetles, they damage wood but don't eat it.
That's right. They use wood for shelter, not food. Carpenter ants excavate galleries, often leaving behind sawdust like frass. Powder post beetles turn the wood into fine powder, leaving small exit holes. Both can cause significant damage if left unchecked. Their tunnels often cut across the grain, which can help differentiate their damage from termites.
And finally, those marine organisms, mollusks and crustaceans, a very specific threat for wood in saltwater. How do you stop them?
For timber used in salt or brackish water like pilings, docks, the best defense, according to our research, is heavy, thorough treatment with coal tar creosote or creosote coal tar solutions. These oil-based preservatives are highly effective at repelling or killing these marine borers.
It's clear that specific treatments are often necessary to really protect wood long term. Our research confirms wood can be treated to prevent or delay damage from fungi, insects, bacteria, marine life, and even fire. It divides preservatives into two main camps: oil type and waterborne. Let's look at the oil types first, starting with the classic, maybe notorious coal tar creosotes. What are their pros and cons?
Coal tar creosote is that black or brownish oil from distilled coal tar. Its main advantages are that it's highly toxic to most wood destroyers, it's insoluble in water so it doesn't leach out easily, and it's relatively simple to apply.
But the downsides?
Significant downsides, especially for occupied buildings. It has a very strong, unpleasant, persistent odor. You absolutely cannot paint over it effectively, and ironically, it's flammable when freshly applied.
So, best for things like
Railroad ties, utility poles, marine pilings, heavy-duty outdoor applications where smell and appearance don't matter as much.
what about the other creosotes mentioned from wood or oil gas, or the creosote solutions? Are they just weaker versions?
Essentially, yes. Our research notes that creosotes from other sources, or solutions diluted with petroleum oils, share the same general characteristics but are considered less effective than pure coal tar creosote. They might be used for less demanding situations.
And then pentachlorophenol, penta, used a lot historically, now mostly for utility poles. What's its story?
Penta is a petroleum oil solution containing 5% pentachlorophenol. It offered good protection against fungi and termites. Key advantages over creosote were that it could be painted, it didn't have the strong odor, it left a clean brown surface, and was less flammable when fresh.
So why isn't it used more broadly now?
Primarily due to health and environmental concerns that led to restrictions on its use. It was widely used from the 1930s for general lumber, but now it's almost exclusively for utility poles and crossarms. And like the source notes, it's less effective against marine borers than creosote.
Okay, let's switch to the waterborne preservatives. First, chromated zinc chloride, CDC. What's its profile?
CZC offers protection against decay, insects, and even some fire resistance. Big pluses. It can be painted, and it has no objectionable odor.
Sounds good. What's the catch?
The catch is significant for outdoor use. Wood treated with CZC cannot be used in contact with the ground or water. The chemicals can leach out in those conditions, so it's for above-ground applications only.
Right. Now the big ones: ammoniacal copper arsenate, ACA, and chromated copper arsenate, CCA. Our research flags these as really important. What makes them stand out, especially this fixation process?
ACA and CCA are workhorses. They're dissolved in water for pressure treatment, and the treated wood is clean and odorless. The key is fixation. After treatment, the chemicals react with the wood components and become chemically bonded or fixed within the wood structure.
Meaning they don't leach out easily?
Exactly. Highly leach resistant. This makes the wood safer for human contact once dry and very durable. Both offer excellent protection against decay, and insects are paintable and odorless.
How do ACA and CCA differ in use?
ACA can be used in contact with the ground and is generally recommended for contact with water, so it's good for demanding applications like foundation posts or even marine use.
And CCA?
CCA has had an incredibly broad range of uses listed: guide rails, utility poles, bridge timbers, piles, glulam beams, landscape timbers, boardwalks, wood foundations, residential decking, fencing, you name it. It's been hugely popular due to its effectiveness and versatility. Although, as noted, its use in some residential applications like decks has faced increased regulation more recently due to the arsenic content.
Okay, so we have the chemicals. How do they actually get into the wood? Our research lists several application methods, from pressure treating down to just brushing it on. What's the range?
The application method drastically affects how well the preservative works and how long it lasts. Pressure treatment. This is the best method for deep, thorough penetration. Wood goes into a cylinder, air is vacuumed out, and preservative is forced in under high pressure. Gets it deep into the wood fibers. Gold standard. Hot and cold bath. Mostly used for creosote. Wood sits in hot preservative, then quickly moved to cold. The cooling creates a vacuum that sucks preservative in. Better than dipping, not as good as pressure. Dipping immersion. Just a short soak in hot preservative. Provides some surface penetration, better than brushing. Brushing, the simplest method, just painting it on, offers only superficial, short-term protection because it doesn't penetrate deeply.
So the deeper the penetration, the better the protection. pressure treatment is king for longevity.
Absolutely, especially for wood facing tough conditions.
We talked about wood's natural charring ability, but you can also treat wood specifically to make it more fire resistant. Our research outlines two main ways: covering it with a compound or impregnating it with chemicals. How does covering it work, and what's its main limitation?
Right. Covering involves applying a fire retardant coating or layer to the wood surface. These coatings work by slowing down the temperature rise when exposed to fire, which reduces flame spread across the surface and slows heat penetration into the wood.
So it buys time.
Exactly. But the big limitation is durability, especially outdoors. These coatings are generally good only for interior use. They just don't hold up well to weather exposure. Rain, sun, humidity will degrade their effectiveness.
What kind of chemicals are in these coatings?
Often water-soluble chemicals like ammonium phosphate, borax, sodium silicate, usually in proprietary blends with binders for adhesion and appearance. There are also some less soluble ones like zinc borate or chlorinated compounds used in more durable coatings, but still mostly for interiors.
Okay, and the second method is impregnation, forcing chemicals into the wood structure. How does that provide fire resistance?
Impregnation aims to change the wood's chemistry so it doesn't readily support combustion. Chemicals are forced deep into the wood, often via pressure treatment. When heated, these chemicals interfere with the burning process. They might release non-combustible gases, promote charring instead of flaming, or release water vapor.
What chemicals are typically used for impregnation?
Common ones listed are ammonium phosphates, monobasic and dibasic, ammonium sulfate, borax, boric acid, and zinc chloride. These salts are effective fire retardants when infused into the wood fibers.
And our research lists some brand names for pressure-treated wood, often associated with these treatments: womanized, tannalized, permanized, bulletin.
Yes, those represent specific proprietary treatment processes and chemical formulations used in the industry. Womanized uses Woolman salts. Tannalized uses Tannolith G salts. Permanized uses BS25. Bulletin is another recognized brand. They signify wood treated to certain standards for preservation or fire resistance.
Okay, we've covered solid wood extensively. Now let's move into engineered wood products, or wood composites. Our research defines them as products made from wood mixed with other materials, usually produced in large sheets, like 4 by 8 foot panels. The most common one has to be plywood. How is it made, and what's the clever trick that makes it so stable?
Plywood is named for its construction. It's made from thin layers, or plies, of wood veneer glued together. The absolute key, the ingenious part, is the grain orientation.
How so?
Each ply is laid so its grain runs at a right angle 90 degrees to the grain of the ply below it. You have the outer layers, the face and back, and the inner layers, the core. This cross-graining is what gives plywood its strength and stability.
So what are the actual benefits of layering it like that? How does it improve on solid wood? This seems like a core engineering principle.
It overcomes several limitations of solid wood. First, it roughly equalizes the strength along the length and width of the panel. Solid wood is strong along the grain, weak across it. Plywood is much more uniform. Second, it's much more resistant to checking and splitting. The cross layers prevent cracks from running easily. Third, and crucially, it's much more dimensionally stable. It shrinks and swells far less with moisture changes because the layers restrain each other. That's a huge advantage for flat panels.
Definitely. So given that stability, what are the typical sizes and uses for different plywood thicknesses? Practical stuff for builders.
Standard panel sizes are usually 3 by 6 feet or the very common 4 by 8 feet. Thickness dictates use. Thin stuff like 316, 4.5 millimeter, or 106.0 millimeter is often for things like double wall partitions, ceilings, cabinet backs where you need coverage but not huge strength. Medium thicknesses like 38 hours, 10.0 millimeters, and 12.0 millimeters are common for drawers, shelves, basic cabinet construction. 3/4 19.0 millimeter is a very common robust thickness for sturdy shelves, cabinet doors, closet doors, furniture parts. And thicker one, 25.0 millimeter, is used for heavy-duty doors or often as subflooring, providing a strong flat base.
And our research lists different types: ordinary, form, marine, and fancy plywood. What makes marine plywood special? What's fancy plywood?
Marine plywood is all about water resistance. It's made with waterproof glue and usually higher quality veneers with fewer voids. It's designed for boat building or architectural uses where it will be exposed to significant moisture, resisting delamination much better than ordinary plywood.
Okay. And fancy.
Fancy plywood is purely about looks. It has a high-quality decorative face veneer made from attractive wood species. Our research lists examples like Nara, Calanthus, Tangil, Lowan, Dow, rosewood. These are used for fine furniture, cabinetry, wall paneling, where the wood grain itself is the main feature.
Right, next composite. Hardboard, often called masonite after its inventor. How is this different from plywood? How's it made?
Hardboard is quite different. It's made by breaking wood chips down into fine individual fibers. Think almost like pulp.
Okay.
This fibrous pulp is then formed into mats. The natural lignin in the wood, sometimes with added binders, helps hold it together. Then these mats are pressed under extremely high heat and pressure between smooth metal plates.
Which makes it dense and smooth.
Exactly. It creates dense, rigid panels. A key characteristic is that they are grainless and usually have one very smooth, often glossy side and one textured or screened side from the manufacturing process. They also add moisture back in a controlled way afterwards to help prevent warping.
And the main advantage, according to our research, is cost. Cheaper than plywood if you don't need maximum strength.
That's often the case, yes. It's an economical choice for things like cabinet backs, drawer bottoms, or wall paneling where a smooth surface for painting is needed and high structural strength isn't the priority. And yes, that smooth side-screen side difference is the dead giveaway for identification. Masonite is just a common brand name for this type of hardboard.
And there are different types: standard, panel, and tempered. What's the difference?
They vary in density and durability. Standard hardboard, light brown, fairly hard, flexible, good for general interior use where it won't get wet. Panel hardboard, denser than standard, a bit tougher. A middle ground, tempered hardboard. This is the toughest type. It's standard hardboard that's been impregnated with oils and resins and then baked. This makes it much denser, harder, stiffer, darker brown, and significantly more resistant to moisture and abrasion.
So tempered is the one for exterior use or wet areas.
Exactly. Ideal for exterior siding components, soffits, or even bathroom linings where moisture resistance is key.
What about sizes and finishes? And any other brand names?
Usually comes in 4x8 foot sheets. Common thicknesses are 18 316 pillars or 14 tickles. You can get it plain, textured, or perforated like pegboard. Besides masonite, our research mentions Lawanit, standard and tempered, and Lawanix, panel boards, as other common brands.
Next up, chipboard. The name pretty much says it all, right? Made from wood chips.
Exactly. Chipboard, or particle board as it's very commonly known, is made by mixing wood particles, chips, shavings, even sawdust with an adhesive, usually a synthetic resin like urea formaldehyde or phenolic resin.
And then pressed together.
Right. The mixture is formed into a mat and then pressed under heat and pressure to create a rigid board. It's often faced with a veneer or laminate for a better appearance. It's a great way to use wood waste efficiently.
And it comes in different densities.
Yes, typically normal, medium, and high density. Normal density is softer, maybe a bit flaky. High density is very solid and hard, often used for things like kitchen worktops or the core material and fire-rated doors because of that density. Hashtag 3.5. Fiberboards and medium density fiberboards, MDF.
Let's talk fiberboards now, and then specifically MDF, which seems to be everywhere these days. What are general fiberboards made from, and what are they typically used for?
General fiberboards, sometimes called insulation board, are often made from various vegetable fibers. The research mentions corn or sugarcane stalks, bagasse as examples, along with wood fibers. They're pressed into sheets.
Are they strong?
Not particularly strong structurally. Their main advantage is good insulating properties. So they're most often used for ceiling tiles or panels, where lightweight and insulation are beneficial. Standard sizes are usually 4x8 feet, in thicknesses from 316 powers up to 34.
Then there's a special acoustic fiberboard.
Yes, that's designed specifically for sound absorption. Made from similar fiber materials, but often pressed with holes or slots in the surface to help trap sound waves. Thicknesses range from 12 up to 2 hours for varying acoustic performance. Brand names like Celotex, Canex, Homosote are associated with these types of fiberboards.
Now, medium-density fiberboard MDF. How is this different, and why is it often preferred over plywood or chipboard for certain things? This feels like a real engineered wood superstar.
MDF is a specific type of fiberboard made from very fine wood fibers, bonded with resin under heat and pressure. It's much denser and more uniform than standard fiberboard or chipboard.
What are its key qualities?
It's dense, very flat, stiff, and crucially, it has no knots or internal voids. Because it's made from such fine, uniform particles, it doesn't have a discernible grain direction.
Which means you can machine it easily.
Exactly. You can cut, route, shape it in any direction without worrying about splintering. It produces incredibly smooth, sharp edges when machined properly, often much better than plywood or chipboard edges.
So perfect for...
Perfect for things like cabinet doors, furniture, moldings, anything that needs a smooth, stable surface for painting or laminating, and where intricate shaping might be required. Its uniformity and smooth finish are its biggest advantages.
Okay, let's shift gears from wood-based panels to gypsum boards, what most people call drywall or sheetrock. Our research calls them non-combustible boards with a gypsum core wrapped in paper, designed for drywall construction, replacing wet plaster. Hugely common for walls, ceilings, partitions. Brands like Boral, Elephant are mentioned. Let's start with the edges. Square edge chassis versus tapered edge. Why the two types?
The edge type dictates how the joints between boards are finished. Square edge, as S boards butt up against each other, leaving a visible square joint. This is used when you plan to cover the joint with a trim strip, cover strip jointing, or if you want the joints to be expressed as part of the design. Tapered edge, TE, is the standard for creating smooth, invisible joints. The edges are slightly thinner, creating a shallow recess when boards are butted together. This recess is filled with joint compound and tape, then sanded smooth, making the joint disappear completely after painting. That's the typical drywall finish we see.
Makes sense. And our research lists a whole bunch of specialized gypsum board types. Wall board, backing board, core board, type X, water-resistant, sheathing, form board. It's clearly not a one-size-fits-all material. Can you break those down?
It really shows the versatility. Let's see. Wall board, your standard stuff for finishing walls and ceilings. Comes with regular paper, foil-backed for vapor barrier insulation, or pre-decorated with vinyl or paper already on it. Backing board, used as a base layer in multi-layer systems for better fire resistance or sound control. Core board, thicker or laminated 12 layers, used as a base in studless partition systems, saving space. Type X gypsum board. This is specifically fire rated. It has glass fibers or other additives in the core to make it resist fire longer. Essential for meeting building codes. Water-resistant backing board, often called green board or blue board, has a water-resistant core and paper facing, used as a base for tile in damp areas like bathrooms or showers. Not waterproof, but water-resistant. Gypsum sheathing, used on the outside of wall framing for fire resistance and bracing. It must be covered by exterior siding or finish, as it's not weather-resistant itself. Gypsum form board, a specialized board used as a permanent form for pouring gypsum concrete roof decks. Stays in place after the concrete cures.
Wow. So much specialization hidden behind a simple painted wall. Hashtag TagShag 3.7. Fiber cement boards. Okay, another board type gaining popularity. Fiber cement boards. Known for being tough. What are they actually made of?
Fiber cement boards get their toughness from their composition. Our research says it's about 72% Portland cement, the binder, 20% mineralized cellulose fibers, often recycled for reinforcement, and about 8% calcium carbonate as a filler.
So, mostly cement with fibers mixed in.
Essentially, yes. That combination makes them very resistant to moisture, rot, insects, and fire. Very durable for exterior siding, soffits, trim, and even interior uses like tile backer board. Hashtag 3.8 particle board.
And just to quickly clarify, particle board again, it sounds like chipboard, but is there any difference in the composition mentioned?
The terms are often used interchangeably, and the composition is very similar. Made from small wood particles, chips, but our research also explicitly lists other proto-materials like cotton stalk, rice straw, bagasse from sugarcane, sawdust bonded with glue under heat and pressure.
So again, using wood waste and other fibrous materials efficiently.
Exactly. An economical panel for non-structural uses, like furniture carcasses, shelving cores, underlayment.
We've covered the structural and panel uses of wood and composites. Now let's get to the finishing touches. Millwork. Our research defines this as finished lumber that's been further processed at a mill cut, shaped, profiled. This is your doors, windows, moldings, trim, the ornamental stuff.
Where the craft really shows. It adds the character and detail to a space. And the choice of wood often depends on whether you plan to paint it or stain it to show the grain.
Our research lists a whole slew of basic molding types. Crown, bed, cove, quarter round, half round, nose and cove, stops at grain molding, panel strip, picture molding. Let's quickly go through their typical uses. Where do these pieces actually go?
Each has a specific job, functionally or aesthetically. Dowel. Simple round rod used to cover joints sometimes. Quarter round, half round. Used to finish inside corners, soften edges. Base shoe is a common quarter round use, trimming the baseboard at the floor. Crowns, decorative, used where wall meets ceiling or top cabinet mantles. Caps. Finish the top edge of windows, doors, wainscoting. Sill. The bottom horizontal ledge of a window or door opening. Stool. The interior shelf-like trim at the bottom of a window, casings, frame windows and doors covering the gap between the frame and the wall, chair rail, protects the wall from chairs, visually divides the wall, typically about 3 feet off the floor, stops, thin strips inside door window jambs to stop the door window sash, panel strip, covers joints and decorative paneling, bases baseboards, trim the wall where it meets the floor, coves, concave profile used for inside corners like a reverse crown, corner for finishing and protecting outside corners, screen, small molding to hold screening and frames.
That's a whole vocabulary just for trim. And our research adds some practical tips for installation, like applying trim after walls and floors are finished, and how to handle joints.
Right. Application details matter for a professional look. Applying trim last ensures a tight fit to finished surfaces.
And those jointing techniques.
For cornices at the ceiling, you can cut the top back slightly to hide ceiling imperfections. A cupped back on wide trim helps it conform to slightly uneven walls. Casings are essential to hide that gap around window door frames. Baseboards cover the wall floor joint. Flexible base shoe helps follow uneven floors. Chair rails often cap wainscoting. Picture moldings provide a way to hang pictures without wall damage. For joints, inside corners of profiled moldings are typically coped one-piece cut to fit the profile of the other. Joints in long, straight runs are face-mitered cut at an angle to make the seam less visible.
And the research mentions built-up cornices.
Yes, that's combining multiple standard molding profiles like a crown, a cove, and a flat strip to create a much more complex decorative cornice effect. Shows the real artistry possible.
Okay. From the ancient craft of wood millwork, let's leap into the modern era with plastics. Our research starts by saying plastics is more of a commercial term than a strict scientific one. So what are they, fundamentally? Where do they come from? It seems like alchemy sometimes.
It's complex chemistry for sure, but basically plastics are synthetic man-made. Their key feature is they can be shaped or molded at some point during manufacturing. That sets them apart from natural materials like wood or metal.
And they come from?
Amazingly common stuff. Coal, salt, natural gas, cotton, wood, even water. These basic substances are chemically transformed into simple units called monomers.
Okay.
Then, through processes like polymerization, these monomers link up into incredibly long chain-like molecules called polymers. Polymers are the fundamental structure of all plastics.
So these long polymer chains give plastics their properties, like being moldable.
Exactly. The nature of these chains dictates the properties. They generally don't stretch much, but they can be molded, extruded into pipes or films, cut, machined into almost any shape, rigid or flexible. And the range of properties is staggering: hard, soft, clear, opaque, heat-resistant, easily softened. That's why they're everywhere in architecture now. Hashtag 5.2, classification of plastics.
That versatility is key. How are plastics broadly classified? Our research mentions 3 types based on origin, but then breaks down the synthetic resins based on how they react to heat. That seems like the crucial distinction for building use.
It really is. The broad categories are cellulose plastics from plants, synthetic resin plastics, man-made chemistry, and some derived from proteins or natural resins. But for architecture, the vital split within synthetic resins is thermoplastics. These soften when you heat them and harden when they cool. You can repeat this process, melt them down, and reshape them. Think recyclable. Their molecules are like long threads that can slide past each other when hot. Thermosetting plastics. These are different. Once they're molded into shape with heat and pressure, they undergo an irreversible chemical change. They set permanently. You can't remelt and reshape them. Their molecules form a rigid, cross-linked 3D structure.
So thermoplastic means remeltable. Thermosetting means permanent set. Got it. That difference must dictate how they're used.
Absolutely. It affects everything from manufacturing processes to end-use applications and disposal. Hashtag 5.3, examples of thermoplastics and their architectural uses.
Okay, let's look at specific thermoplastics, the remeltable kind, and their uses. First up, acrylics, like lucite or plexiglass, known for being clear, right?
Yes, their big selling point is combining glass-like transparency with being shatterproof, a big safety plus. They aren't as scratch-resistant as glass, though.
Where do we see them?
Ski lights, sky domes are classic uses. Also, safety glazing, paints, adhesives, some hardware, and very commonly in lighting fixtures for diffusing light.
Cellulosics, like cellulose acetate.
Those are mainly used in coatings, paints, lacquers, and for making transparent sheeting or films.
Polyethylene, PE. Super common. Our research mentions Ziegler PE and ICI PE. What's the difference?
It's about density. Siegler PE is high-density polyethylene, HDPE, hard, strong, rigid, used for things like durable containers, some pipes. ICIPE is low-density polyethylene, LDPE, more flexible, tough, resilient.
And in construction.
LDPE is widely used as pond liners, but critically, as vapor barriers and damp-proofing membranes under slabs or in walls. That flexibility and impermeability are key.
Polystyrene. Research says it's sensitive to solvents, but still very important.
Why? Despite solvent sensitivity, it's valued for its excellent transparency, rigidity, and ease of molding. You see it in things like wall tiles, though they can be brittle, lighting diffusers. But its most important use is probably as foam expanded polystyrene, EPS, or extruded polystyrene, XPS, which is a major thermal insulator, huge in construction now, also used in some concrete paints.
Polyvinyl chloride, PVC. Everyone knows PVC pipes. What else?
PVC is rigid, tough, solvent-resistant, and importantly, flame-resistant. Besides pipes, it's used extensively for resilient floor tiles, films, as a component in paints and adhesives, and even in laminated safety glass layers. Very versatile and durable.
Polycarbonates.
Yeah.
Described as linear polyesters.
Yes, known for being extremely tough and strong, with good heat resistance, up to 150 degrees C, and excellent dimensional stability. Great impact resistance.
Oh, uses.
Often injection molded for parts that need to be strong, replacing die-cast metal sometimes. Also very common for durable skylights and safety glazing because it's so tough and clear.
Polypropylene.
Another tough plastic, noted for good resistance to heat and chemicals. Used in some piping, containers, automotive parts, even fibers for carpets or ropes.
Nylons or linear polyamides. What are their key features?
Nylons are known for being exceptionally strong, elastic, abrasion-resistant, and resistant to chemicals and oils. Easy to wash, can be dyed many colors. Used in textiles like carpets, but also for durable mechanical parts like gears or rollers and some hardware.
Fluoroplastics. Research highlights their abrasion resistance.
Yes, that's a key feature. They have fluorine atoms replacing hydrogen, giving them excellent chemical and heat resistance, good electrical properties, and very low friction, along with wear resistance. Think Teflon coatings, PTFE is a fluoroplastic, high-performance wire insulation, seals.
And finally, acrylonitrile butadiene styrene ABS, another common one.
ABS is known for its toughness, heat resistance, and high-gloss finish. Good dimensional stability, easy-to-injection mold. Widely used for appliance housings, furniture parts, automotive components. It also has good strength for making extruded sheets, which are then thermoformed into larger items like hot tub shells or parts for RVs. A good all-around tough plastic. Hashtag tag 5.4. Examples of thermosetting plastics and their architectural uses.
Okay, that covers the thermoplastics. Now for the thermosets, the ones that set permanently, let's start with melamine and urea.
These are hard, durable, stable thermosets, resistant to chemicals, heat, electricity. Melamine is famous for molded dishes, very hard and dishwasher safe. Urea is good for diffusing light from incandescent bulbs, doesn't yellow easily, and is used in hard, durable, baked enamel paints.
Epoxy. We know it as a super strong glue.
Yeah.
Other uses.
Its adhesive quality is key in construction for bonding things strongly. Also used in highly chemical-resistant paints and coatings, and for durable caulking compounds where a strong, permanent seal is needed. Primarily used for molded electrical insulation parts. Also, very importantly, as the resin binder vehicle in many oil-based paints, enamels, and varnishes, providing durability and gloss.
Phenolics. Often dark-colored, right? Like Bakelite.
Yes, phenolics like Bakelite were early plastics, still used for paints, baked enamels, strong adhesives, also used to impregnate paper or wood to make dense, hard materials like countertop bases or electrical boards, and for some durable hardware components.
Polyester. Our research mentions those big translucent panels often reinforced with glass fiber.
That's a major use, corrugated or flat panels for skylights, awnings, greenhouses. They're strong, rigid, impact resistant. Polyester resin is also used for impregnating paper and wood as a laminating material, like in fiberglass boat hulls, and as a contact adhesive.
Urethanes, what about them?
Urethanes are versatile, used as tough, flexible coatings and paints. Also widely used as foams, often spray-applied or rigid boards for excellent thermal insulation. The foam can be self-adhesive too.
And lastly, silicones. What's their architectural niche?
Silicones are known for stability over a wide temperature range and excellent water resistance. Used primarily as clear water-repellent coatings for masonry and concrete, they soak in and stop water absorption without changing the look much. Also crucial for high-performance sealants and caulks due to their flexibility and weather resistance.
So plastics aren't just molded parts. They come in sheets, films, foams too. Let's look at plastic sheets first. Usually acrylate, polyester, polystyrene, flat or corrugated, maybe reinforced. What are they used for?
They offer alternatives to other materials, can replace glass in windows, doors, shower enclosures, skylights especially, where shatter resistance or lightweight is needed. Available clear, translucent, opaque, colored. Corrugated plastic sheets are common for roofing on sheds, patios, greenhouses. Very versatile sheet material.
And film sheets. Our research flags these for water barriers and damp proofing. What are the details there?
Yes, thin plastic films, usually polyethylene or polyvinyl, are critical for moisture control. They come in rolls, typically 1 to 10 mils thick. A mil is a thousandth of an inch. Common construction thicknesses are 2, 4, or 6 mils.
How are they used?
Laid down under concrete slabs, usually 4 mil over sand, 6 mil over gravel, to stop moisture rising from the ground. Also used within wall assemblies as vapor barriers. The key is using wide sheets to minimize seams and overlapping any joints by at least 6 inches and sealing them to create a continuous barrier.
Got it. And plastic foam. We mentioned polystyrene foam for insulation. Other uses?
Foams have trapped gas bubbles, making them lightweight and good insulators. So yes, thermal insulation is a huge use. Polystyrene, polyurethane, etc. Also used for flotation and for shock absorption or cushioning, maybe under flooring or for packaging delicate equipment. The potential for lightweight structural panels using foam cores is also significant.
Another way to combine materials is lamination. Our research defines it as layering paper or fabric impregnated with thermosetting resins. How does that process work?
You take sheets of a base material, paper or cotton cloth are common, and saturate them with a thermosetting resin like melamine or phenolic. Then you stack these sticky sheets together.
How many layer?
The number of layers determines the final thickness. This stack is then put into a press under high heat and pressure. The resin cures, bonding all the layers into a single, hard, solid sheet.
And the most common use is decorative laminates, like for countertop.
Exactly. Decorative laminates are huge for countertops, tabletops, cabinet faces, wall panels. They have a decorative top layer with a printed pattern, wood grain, stone, solid color protected by a tough, clear wear layer, all bonded to core layers of resin-impregnated paper. They give the look of other materials, but with much higher durability, scratch resistance, and ease of cleaning. Very practical and versatile.
Okay, last major material, glass. So fundamental to architecture for light and views. Our research starts with 3 basic types, representing a sort of quality progression: sheet, float, and plate glass. What's the difference?
It's mainly about the manufacturing process and the resulting flatness and clarity. Sheet glass, made by drawing molten glass upwards. This older process inherently creates some waviness or distortion, especially noticeable in larger pieces. Float glass. This is how most flat glass is made today. Molten glass is floated on a bed of molten tin. Gravity makes it perfectly flat and smooth on both sides. Minimal distortion, no need for grinding or polishing. Excellent clarity. Plate glass. Traditionally, this was made by casting, rolling, then grinding and polishing both sides for superior optical quality. Very clear. Virtually no distortion. But float glass achieves similar or better quality much more efficiently now, so true plate glass is less common. What we often call plate glass today is usually thick float glass.
So float glass is the modern standard for high-quality flat glass.
Yeah.
Beyond these basics, though, there are tons of variations with special properties. Pattern, wire, heat-absorbing, reflective, tempered, laminated, insulating glass. Let's quickly cover what makes each special.
These variations allow glass to do much more than just be transparent. Pattern glass has a texture or pattern rolled onto one or both surfaces. Diffuses light, provides privacy. Think bathroom windows. Wire glass has wire mesh embedded within it, holds the glass together if it breaks, improving fire resistance and safety, often required in fire-rated doors or partitions. Heat-absorbing tinted glass contains additives that make it absorb solar heat, reduces heat gain inside the building, lowering cooling costs, usually has a tint, bronze, gray, green, blue. Reflective coated glass has a thin metallic coating that reflects solar heat and light, reduces heat gain even more than tinted glass, often looks like a mirror from outside. Tempered glass, heat treated to make it much stronger and safer. If it breaks, it shatters into small, relatively harmless pebbles, not sharp shards. Used for shower doors, car side windows, glass doors. Laminated glass, 2 or more layers of glass bonded together with a plastic interlayer, usually PVB. If it breaks, the plastic holds the fragments together. Used for car windshields, safety glazing, security glass, sound insulation. Insulating glass, double, triple glazing. 2 or 3 panes of glass separated by a sealed air or gas-filled space. drastically reduces heat transfer, keeping heat in during winter, out during summer, improving energy efficiency and reducing condensation. Started for windows in most climates now.
And then there's glass in block form. Glass blocks let light through but act more like masonry. Used in non-load-bearing walls or window openings. What are their typical sizes? Do the dimensions include the mortar joints?
Yes, the nominal sizes usually do include the standard 14-minute mortar joint, which simplifies layout. Common sizes mentioned are rectangular blocks like 4 by 8 and 6 by 8 inches, and square ones like 6 by 6, 8 by 8, and 12 by 12 inches face dimensions. Thicknesses of 3 or 4 are also noted.
Can you build curves with them?
You can, but there are limits. Our research gives minimum radii, 4 feet for 6 center blocks, 6 feet for 8 blocks, 8 feet for 12 blocks. Any tighter and the joints get difficult. And importantly, curved walls need expansion joints where the curve changes direction to handle movement.
Do they come with different textures or coatings to control light?
Absolutely. You can get various surface patterns, wavy, frosted, ribbed to diffuse light or provide privacy. There are also blocks with internal inserts or special coatings designed to reduce solar heat gain, control glare, or adjust the brightness of the light coming through. Lots of options beyond just clear.
And finally, what are the key construction details? Limits on panel size. How are the edges handled at the head, jambs, and sill? These seem crucial for stability.
Very crucial. There are limits on unsupported panel areas. 144 square feet for exterior walls, max 15 feet in any dimension. 250 square feet for interior walls, max 25 feet. Larger areas need reinforcing stiffeners or shelves.
And the edges.
Head sections, top, need space for lintel deflection, often using expansion strips, sealant, and anchors to the structure above. Jamb sections, A-sides, also need expansion joints with sealant, expansion strips, and panel anchors securing them to the adjacent wall or column. Sill sections, bottom, need proper support, often involving asphalt emulsion for waterproofing under the mortar bed, and sometimes steel channels or angles for solid support. These details ensure the panel can handle movement and remain stable and weathertight. #outro.
So after all that, what's the big picture? We've definitely taken a deep dive into wood, plastics, and glass and architecture, from the tiny cells in a tree and how grain matters to the complex chemistry of plastics.
And the engineering behind making glass work harder in things like insulating units or sturdy blocks.
It really gives you a comprehensive understanding way beyond just surface appearance.
Hopefully. Whether you're maybe planning a project or just looking at the buildings around you with fresh eyes.
Or even if you just like knowing how stuff works.
Right. We hope you've gained a new appreciation for the science, the craft, the sheer ingenuity that goes into using these materials effectively. It's not just what they are, but how their unique strengths are used and their weaknesses overcome to create the spaces we use every day.
So next time you lean on a wooden railing, look through a window, walk on a floor, maybe think about the journey that material took. The sawing method, the seasoning, the chemical treatments, the layering.
All those hidden properties and processes we discussed.
And think about the future. What new ways will architects and engineers find to push the boundaries with these seemingly ordinary yet incredibly versatile materials?
And how will we balance the use of natural materials like wood with the performance of synthetics like plastics, especially as we think more about sustainability and the impact of our buildings? What will the innovative, sustainable structures of tomorrow be made of? Something to ponder.